Hello and welcome to Lesson 3 in Module 1. In Lesson 3, we will look at geometric interpretation of the solutions of a linear system. So, you should have your student notes ready to go here to follow along with me. And again, as I do questions, please feel free to pause the video for yourself, do the question first, and then check your answer against mine. Okay, it's a good way to learn this stuff, and it helps to get you more interacting with the math, which will again help you to understand it and learn it better when you struggle with it first, before then waiting to see the answer in my explanation. Of course, you can also wait and see one or two examples before you then try stuff on your own. Okay, so but use your best judgment, and again, try and challenge yourself to do these problems on your own first before you have me do them for you. Okay, so what we're going to actually do here is jump down to near the end of these practice exercises and go to this summary lesson summary right here. Okay, and we'll use this to kind of kick us off. So when the graphs of a system of linear equations are sketched, and a system of linear equations is just more than one equation, more than one linear meaning just line. The graph of these equations are lines. You can see right here and right here, right? And it's a system again because there's more than one equation together simultaneously. We're solving them together. Okay. Anyway, when the graphs of a system of linear equations are sketched, and if they are not parallel lines, then the point of intersection of the lines of the graph represent the solution to the system. Okay, kind of like X marks the spot. So boom, right there, where those two lines intersect, 4, -1, that's the solution. Two distinct lines intersect at most at one point if they intersect, right? Think about that. Can you imagine two lines intersecting in more than one place? Right? And in the plane like this, the answer is no, right? We're going to keep going in this direction, keep going this direction, keep going this direction, keep going this direction, and they're never going to intersect. Again, they only intersect at this one point right here. Okay? The coordinates of that point represent values that make both equations of the system true. So in other words, this coordinate here, 4, -1, it works in this equation and it works in this equation. And what do I mean by work? I mean you can substitute in that point into the two equations, and here they do that for you right here. You can see that. Okay? They take that point 4, -1. They put 4 in for the x, -1 in for the y, right here like this, and then you just add 4, -1, and you get 3 = 3. So check, that makes the equation true. Likewise here with the x minus y = 5, put 4 in for the x, -1 in for the y. Minus and negative, remember that becomes plus positive, so 4 + 1 is 5, and 5 = 5, check. Okay, that works. No other coordinates in the entire coordinate plane will make both of these equations true. So with that being said, let's take a look at our first example up here. So example 1, we are asked to sketch the graph of these two functions. Now, when it comes to sketching the graph of a linear equation, we may need a little bit of a mini lesson on that too, right? Let's do this second equation because it's already in the nice slope-intercept form. Or y = mx plus b, where the slope is m and the y-intercept is b. So looking right here, right, what is the slope of that second equation? What's the slope of this equation right here? What's the m, right? The m is 4. Okay, so the m in this case, 4. Actually, I'll do that over here. And what's the y-intercept? What's the b over here? Well, it's 3. Okay, so the b is the y-intercept, which means that's where the graph crosses the y-axis. So there's 3 on the y-axis. And then the 4, that slope, remember the slope describes how the line changes, how it goes up or goes down and goes left or goes right. And so remember, this is rise. And I didn't really leave myself much space here. Let's see if I can kind of like make this go down here. There you go. Rise over run. Okay, like that. So from this point right here, we're going to count up 1, 2, 3, 4 for this rise of 4 here. And we'll go 1 to the right because a positive 1 means you go right 1. And so this will be our new point here. I'm going to get rid of those. Whoops. I'll get rid of those lines. I can't really go any further. I kind of run out of space up here. So instead I'll go, you can also go in the opposite direction, exactly opposite. So instead of going up 4, right 1, you can also go down 1, 2, 3, 4, and then left 1. Put a point right there, and we can connect these dots. Okay. Any point on this line solves this equation. Now, we also want to graph this, but this first equation is not in slope-intercept form. Right? Slope-intercept form requires that we have y by itself. So what can we do to this equation here to get the y by itself? What's with the y that we need to get rid of? Well, the answer is the x. So we'll subtract x on both sides. Negative 2 minus x, those are not like terms, so we'll just rewrite negative 2 minus x like that. Okay? So here we have to be a little bit careful because the order is different. In the first equation, the x came first and then the b, but in this case, the x is second. What's the number in front of this x right here? Will be a 1, right? And since it's a minus 1x, the slope then, the m, is negative 1, or as a fraction, negative 1 over 1. So there's our rise, and there's our run. This negative 2 then is our b, our y-intercept. So negative 2 is the y-intercept, and the rise is negative 1, so down 1, and the run is positive 1, so right 1. And then up 1, left 1, and aha, we can see where they're going to intersect. And then up 1, left 1, up 1, left 1, because again, we can go in the exact opposite direction too to extend that line. And voila, there's the solution to our system at the point negative 1, 1. Sorry, negative 1, I should say. Okay. Oops, here, I did it right here is where I'm supposed to put it. Okay. Verify is a solution to this equation right here. So I'll just plug in negative 1 for the x-coordinate, negative 1 for the y-coordinate, and we'll see if it equals negative 2. Negative 1 plus negative 1 is negative 2. So check, it works. And then the one is verified in the other equation right here. So we'll put negative 1 in for y, negative 1 for x, and simplify. 4 times negative 1 is negative 4. Negative 4 plus 3 is negative 1. And voila, yes, it works. Check. Could the point negative 4, 2 be a solution to the system of linear equations? Well, let's try it in this equation and see if it works. Four times negative 4 is negative 16. And right away you can kind of see, this is not going to work. Negative 16 plus 3 is negative 13. And those are not equal to each other. So, no. The coordinate negative 4, 2 does not work, or does not solve y equals 4x plus 3. So it cannot be a solution to the system. I'll just say a solution. Okay, we'll stop right there, and I'll do the next two examples in the next video.